Hey students, great. I just got a new question when I haven't made a video here before, so I thought I would make another video, and it's a good one on using Gauss's law. It also has conductor in it, and it's just all around good. Surprisingly, there's not a whole lot of math, so watch this one. It's a lot more of reading the math than doing the math, as I keep saying. You want to make sure you be able to do both. Not just do the math, but also read it. What does it really mean? Watch here. It says a long, straight wire is surrounded by a hollow metal cylinder whose axis corresponds with that of the wire. Okay, so if I kind of read into that, here will be this wire. It's really long. And so a long straight wire is then surrounded by a hollow metal cylinder. Okay, so this metal wire has a cylinder on it. And it probably doesn't look very good, but I'm hoping you see something like this. Let's see, where's my my little demo stuff? Here we go. Why don't I use, hey, where'd it go? Here. So why don't I use this for my wire, okay. And then I'll use this for my three-dimensional cylinder that is hollow. So there's the hollow. Now it does have a little bit of thickness, and that's what I'm trying to draw right here. And so this wire is in the middle. And we haven't gotten that far in this semester yet, but we're about to. We call this a coaxial cable because you can send down the current down one and return down the other, and they're coaxial. The symmetry of them match off. So this is the idea, and what I want you to see then is in here would be a solid metal piece. Then there is kind of this hollow place, and so maybe if I kind of hold it up at the camera, if there's enough light, you can kind of see there's this hollow place around the center conductor. Then there's some thickness, which would be the thickness of this piece of paper here. And then there's the outside. And so like all of our problems, the first step is to kind of really understand what they're talking about here, okay? Oh, and I shouldn't have drawn it in blue. Forgive me. Bummer. Because I know in class I've been trying to do Gaussian surfaces in blue, and I should have drawn it in black. All right, well, so I'm going to reverse those colors here for this problem. I'll do my Gaussian surface. Well, should I do a Gaussian surface? Well, maybe I'll say the orange for the electric field, because I like to do that. And maybe the Gaussian surface I'll do in green. I don't think that'll mess us up. Okay, so a little bit different than the way your author has it color-coded and the way I like to do it on the whiteboard. But hopefully it still kind of makes sense. Now, also it might be nice to kind of picture looking down the top here. All right, so where's the blue one here? So looking down the top, I would have that center conductor, then some space, and then the inner conductor of the hollow cylinder on the outside, but later on we're going to call the shielding wire. And then it has some thickness to it, and so let me give it some thickness. And then we have outside of that, okay? So I think I've, moving along here. So I've got this long straight wire surrounded by a hollow metal. Metal's going to be important. Let's talk about that cylinder whose axis corresponds with that of the wire. Okay. Now, the wire is charged per unit length of lambda. So let me just put a bunch of positives down here, although they don't really say lambda is a positive number. But we'll just give an answer in terms of lambda or negative of lambda if we have some negative charges. Okay, so there's some positive, and so on the top-down picture, I'll just kind of put a plus there. Okay, so the wire is linked to the cylinder, then, until here, has a net charge of 2 lambda. So there's 2 lambdas here. And I won't draw anything because this is kind of what this problem is about. We haven't really got a chance to talk about it, and I want you to think about where would those charges be? It's a total of 2 lambda, but would they be like on this inner surface? Would they be on the outer surface? Would they split 50-50? Would they be distributed within the metal? Where would it be? From this information and from Gauss's law, find A, the charge per unit length on the inner and outer surfaces of the cylinder. So they want us to find where those charges are. The total is 2 lambda, but are they on the inner surface? On the outer? Both? And if both, is it split 50? I mean, how is it split? And then, of course, find the electric field inside the cylinder, a distance r from the axis. I'm sorry, outside the cylinder. And I might just do it in all 3 places. I might say inside the cylinder, in the metal conductor of the cylinder, and then outside, which is what they ask, the electric field outside the cylinder, some distance r away. So let me just kind of move my paper off to the side and say, all right, we're going to do Gauss's law. And Gauss's law says if you integrate the electric field over some closed surface, so that's a flux calculation on a closed surface, it is equal to the charge inside over epsilon naught. And so let's use this in kind of a thinking mode, not necessarily solving mode, but thinking mode. And so let me draw my first Gaussian surface, and that's what I want to emphasize in this problem. I'll probably do a lot of Gaussian surfaces. Maybe the one to do, and so, like I said, I'll do the Gaussian surface in green, is why don't I do a Gaussian surface that is within the hollow part of the cylinder, okay? So I'll make a cylinder. In fact, I'll use this to kind of represent also the cylinder. The cylinder is wrapping around the wire, but it doesn't have a radius quite as big as the inner radius of the hollow cylinder. So in this top-down picture, I guess I'm looking right here. Okay? And if I were to apply Gauss's law, and I hope I don't cheat you too much on this, I would notice right away that according to Gauss's law and this calculation, this says it only matters on the charge on the inside. And that's kind of interesting because we did a problem twice, actually. We found the electric field from a line of charge. Now, we didn't have a hollow conductor around it, but in class and in one of the examples of 24, your author uses a Gaussian surface around a line of charge and finds that electric field. And this problem is only slightly different, but you could even argue not even different at all, because here's the beauty of Gauss's law. We talked about the thinking of Gauss and how he came up with it, and any charges that are outside of the Gaussian surface don't count in the equation. That's because whatever flux they make goes in one side of the surface and out the other. So it's not like they're not important, but for the practicality of doing this, they don't matter. So what I'm going to say is that the charge enclosed in the Gaussian surface is only the charge along this center wire. And so we could go through all the mathematical steps. But since there's a lot to do in those problems, let me just jump right to the answer we got both in class and in example. Oh, and also we did this the harder way without Gauss's law. We did it with Coulomb's law in the last chapter. Now, I don't think I need to box it so much because we're not going to do any calculation, but what I do want you to see is at this point, there really hasn't been anything significant to change or to vary. And so if I were to draw the electric field, so here's kind of this burnt orange, it would be something like this. It would be exactly like we did in class, where we use the symmetry to argue the direction of the electric field. We use the symmetry to argue the strength of the electric field. That allowed us to say that was 0, that was a constant. We pulled it out, and we came up with this, okay? So I'm going to, like I said, not actually derive that one, but just say, okay, there would be the Gaussian surface so far. Now, or the electric field so far. Now, here's really what the problem begins, is because let's look at another Gaussian surface. Let's look at a Gaussian surface that is actually in that little space of the thickness of our conductor. So in this top-down view, it's right here. So let me call this Gaussian surface number 2. And I'm going to go with a little facts that you read in the book. So far this semester, I haven't seen it in the lecture, but you soon will. And that is the argument that the electric field is 0, at least after things settle out inside a conductor. So in other words, if I have a metal conductor, the word conductor means that charges can move if you push on them. So if you have an electric field inside a conductor, that means they would be putting forces on the electrons, and the electrons would move. And then they would move and shuffle around, changing the effect of the field. And when would they no longer be shuffled around? Well, I guess when eventually the force comes out to be 0, which means the electric field comes out to be 0. And that's the argument here, that the electric field inside a conductor has to be 0. So using that and Gaussian surface number 2, let me come back here and write Gauss's law again. And this time I'm going to look at the equation over here on my left. And knowing that the electric field is 0, because I'm in a metal conductor here, okay, so 0, I can say then that if I were to add up all the flux on Gaussian surface number 2, I would just be adding up a bunch of zeros and doing the integral and coming up with a 0. And of course, what we conclude then is the charge inside Gaussian surface number 2 is 0. Now, that becomes very useful because we already said this inner conductor has a charge per length of lambda. And that is inside Gaussian surface number 2. And it also then means that there must be some kind of charge on Gaussian surface number 2, or within Gaussian surface number 2. And since this Gaussian surface number 2 can really be drawn anywhere in the conductor, I'll imagine for a second I drew this Gaussian surface number 2 infinitely close to this inside edge, but still inside the metal conductor. And so I would still say the total charge is 0. And therefore, the only place that the negative charge can be is on the inner surface of the conductor. And so this inner surface must have equal amounts of negative as this center one has positive, so the total can come out to be 0. And so I'm going to say there would be negative lambda on the inside surface. And that was one of the questions here. What is the charge per unit length on the inner? And so negative lambda. And of course, now let's do that same logic for the outer. All right, so coming along here, let's do Gaussian surface number 3. So number 3, I'm going to draw a big Gaussian surface. Another cylinder. This one is going to have a radius bigger than the outer radius of our hollow cylinder. So in this top-down picture, I'm looking at something like this. Okay. And of course, this one here would enclose all of the charges that are on the total of the inside wire and the outside wire. So what they call the hollow cylinder and the wire. Now, bear with me here. I'm going to jump back to Gaussian surface number 2, because remember I said Gaussian surface number 2, if I would imagine drawing it infinitesimally close to the inner surface, I still would get a field of 0 because I'm still inside the conductor. And so the negative lambda can only be on that inside surface. And so that was the clue to me to draw it on the inside surface. But if you kind of imagine taking surface number 2 and draw it infinitesimally close to the outer surface, okay? There too, as long as you're still inside the metal, you would say the field is 0. And so you would still say that the charge enclosed in Gaussian surface number 2 is still 0. And so there wouldn't be any charges within the metal itself. They would only be on the surface. Which, of course, goes really back to this statement also, that the electric field inside the conductor has to be 0. You can't have any free charges floating around. They would make a field. They have to be pushed and migrate to the edges and to the surface. And this is our argument of why they would have to be on the surface. So they can be on the inner surface, so I labeled that. But what that's also saying is the outer surface would have any other charges. And the reason that's important here is they said right here that the cylinder has a net charge of 2 lambda. And we've just argued that the inner surface has a negative lambda. And we also argued that the only other place for charge is on this outer surface. And so knowing that when I put all the charges together on this outer conductor here, the hollow, what they call the hollow cylinder, I have to come up with 2 lambda. And so I already have a negative lambda on the inside. So my conclusion here is the outside surface must have a charge of 3 lambda. Because taking the 3 lambda on the outside and adding it together with the negative lambda on the inside, I have a net of 2 lambda. And of course, that answers this other part of this question right here. What is the charge on the outer surface? And so outer surface is 3 lambda. Again, making a net of 2 lambda. So now that we've answered A, what are the charges on the surfaces of the hollow cylinder, inside and outside, we can go on to say what is the electric field. Now the question just says on the outside, but if it'll be okay with you, why don't I do every area of this? That is, inside this hollow part, inside the metal conductor, and then what they're asking, the outside. And technically I've already done the other 2. And so I'm going to say the electric field, because of surface number 1, is this. I already made that argument. So let me not take more valuable video time and just say, okay, go back to the start of this problem. And you'll see when I drew this surface that I only used the charge on the inside. And you can go back to my examples of getting the electric field from a line of charge. And so even though we have a hollow one around it, we don't pay much attention to it, at least at this point. And so the electric field in this area is this. And I'm sure that's why the author didn't even bother to ask. He was thinking, hey, this is so obvious. Let me not ask about that one. Let me ask about the hard one, which is on the outside. The other one that's pretty easy is Gaussian surface number 2. That is, what's the electric field in the metal conductor of the hollow cylinder. And then again, we said that would have to be 0. So again, maybe that was so obvious. That's why your author didn't even ask, what is the electric field in that area? So finally, you can see, let's do it way out here on surface number 3. So now let's do a calculation. So let me do an integral of E dot dA of the charge inside over epsilon naught. And why don't I call this a 3 down here? Because I'm going to be looking at surface number 3. Okay. And so maybe I'll do the right-hand side first. The total charge inside would be the charge from this inner wire plus the inner surface plus the outer surface. So that's a lambda and then a negative lambda and then a 3 lambda. So when I add that all together, the charge is 3 lambda times the length, and I didn't put that anywhere in my diagram, but however long I make that Gaussian surface. So that's the charge per length, and that's how long it is. Now the other side of the equation, where we take the dot product, has the same logic as we did for a single line of charge, although we do have something more complicated. And so maybe we should go through this one again, because the first thing to do, oops, I forgot to divide by epsilon naught. Let me just copy that down, 3 lambda L over epsilon naught. The first thing to do is to do a symmetry argument about the angle. Okay, so earlier on I was drawing the electric field, and in that case I was looking at only the inside wire. Now let's look at the inside and the hollow cylinder, and let's draw lines of symmetry. Now in class I've been drawing lines of symmetry in red. On this video I don't know if the red and the orange will stand out, but our argument was the electric field has to be along lines of symmetry. And real quickly to repeat that, that's because if you kind of imagine this charge distribution and then you flip it around a line of symmetry, you get the same charge distribution. That's why we call it a line of symmetry. And you can kind of see it here. I've got a plus here, minus here, plus here. If I flip it, all of these go over to here, and all of these kind of tuck underneath and go to here. And you're just going to end up with the same charge distribution. So whatever electric field this created, when you flip it, it better be pointing in the same direction, because you end up with the same charge distribution. You see, the direction of that electric field and the strength of that electric field is determined by that charge distribution. And so this advanced argument of symmetry is really powerful. So imagine flipping it. Since I get the same charge distribution, I should get the same field. And so a field that was, say, pointing off in this direction would not work, because if you flipped it, it now would be pointing in that direction. And how could it point in a different direction before if you have the same charge distribution before and after you flip it? So it's got to point in the same direction. And that can only work when it's along the line of symmetry. Because when you flip something along the line of symmetry, it just kind of rotates. It still points in the same direction. It doesn't kind of pivot as it rotates. Okay? So that's why in class we made the argument using Gauss's law, we are going to look for lines of symmetry. The lines of symmetry will tell us the direction of the field. And so we can conclude that even though our charges are much more complicated than just a single wire, they haven't changed the symmetry because this outer one has this kind of this cylindrical symmetry also. And so when you flip it, you end up with the same thing. So I'm going to use that piece of information to say that I know the electric field way out here. And again, after we consider both the center wire and the hollow cylinder, is radially outward. But that's also the direction of the normal. So we've been doing normal in black. So these would be the normal vectors. And they too would be radially outward. So everywhere along the round parts, and what I do with my cylinder right here, so everything around this round part, which I often call the face, would be an angle of 0 between the field and the normal. 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 The field and the normal point in the same direction. So what I can do here is put a cosine of 0 degrees. Now, by the way, I guess to be completely fair with this problem, I would have to say my Gaussian surface to be closed has a top and a bottom. And on the top, the electric field would be radially outward, but the normal would be straight up, and that's 90 degrees. And so everywhere on the top would be a 0, and likewise for the bottom. So I guess for completeness, I should probably put, this is the integral of the curved face part, but I would get a 0 for the top of the Gaussian surface, and another 0 for the bottom. And so I just want to show you I'm thinking about a fully closed surface. But since there's 0, if I accidentally forgot them, I would be okay. But only by luck. We don't want to rely on luck. All right, so like I said, symmetry, that's a tough one. Now also, another part of this symmetry argument is that if you imagine yourself standing on Gaussian surface number 3, looking at the charge distribution, again, it would be more complicated than just a line of charge like we said before. It would have a line of charge, then it would have charges on an inner surface and charges on an outer surface. But if you imagine standing somewhere else on that Gaussian surface, you would be seeing the same charge distribution, however complex it is. And so the strength of the electric field, which we already said the direction would be outward, but now I'm going to comment about the strength of the field. The strength of the field would be the same on each of them. And in fact, everywhere on this face, I can make that argument. So that means when I do this integral here, I could say this integral is saying that the electric field on the face is a constant. And so I can pull out the electric field. Oh, no longer closed surface because I top and bottom. And then I'd have a dA. Cosine of 0 is 1. And I get 3 lambda L over epsilon naught. And now, not actually doing the integral, but then looking at the geometry here, a picture of it, this Gaussian surface number 3, I can kind of unwrap it, if you will, and its surface area would be this length, which is the circumference of it when I roll it up, and then this part is the L. So the area would be the circumference, 2 pi r, times L. Now the L's cancel off. And one last step here. The electric field then would be 1 over 2 pi epsilon naught 3 lambda over r. And although it took a while to kind of go through all the steps of Gauss's law, I hope you kind of see that they were no different than what we did when we did just the line of charge and we didn't have to worry about the shell on the outside. The only thing that changed was right here when we said how much charge there was. We had a charge density of 3 lambda. But we still had the L and the epsilon naught, and we still had the same looking surface. We still had a top and a bottom, which come out to be 0. We still had total area, which is 2 pi r times L. We also said that the electric field can be pulled out in front, blah, 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 blah. All right, so there it is. And this, and maybe not too much of a surprise, that the electric field simply just looks like a straight wire, a very thin straight wire that has 3 times the charge, and kind of makes sense because this inner one has lambda and this outer one has 2 lambda, total of 3 lambda, and they have this cylindrical symmetry. So as long as you're beyond the second conductor, the outer conductor, the hollow metal cylinder, as your author calls it, you are going to be the same as if you just had a solid wire of 3 lambda. All right, well, wanted to work that one out because it's got some good logic, not a whole lot of math, but some good logic of what is meant by Gauss's law. Oh, wow, took me a while too. So hopefully that's helpful. Well, bye now.